In the 1980s, a team of scientists at the University of Chicago, led by Dr. Alan Rechtschaffen, set out to answer a simple but unsettling question. What happens if an animal never goes to sleep? Their work, known as the Rechtschaffen sleep deprivation study, involved placing rats on a rotating platform suspended over water. Each time a rat began to drift off, the platform would spin, forcing it to stay awake to avoid falling in. And after just 2 or 3 weeks of total sleep deprivation, all the rats died. Their bodies broke down rapidly. They lost weight despite eating more. Their immune systems collapsed. Their internal temperature dropped. And in the end, the cause wasn't any single disease or injury. It was simply the lack of sleep. The message of the study was clear. Sleep isn't optional. It's a biological necessity. But on the opposite side of the animal kingdom, something even stranger was occurring. Aquariums had just begun trying to keep great white sharks in captivity. After all, a live great white would have been worth millions to audiences. But every attempt by the aquariums was ending the same way. The shark kept swimming non-stop until it either injured itself or died. The sharks had no spinning platforms and no external pressure, but they kept on swimming, eyes fully open and aware the entire time, negating everything we thought we knew about logic, sleep, biology, and survival. Even in the wild, the scientists noticed the same thing. The great white sharks never stopped moving. With a brain as advanced as that of a great white, prolonged sleep deprivation would lead to cognitive breakdown, immune failure, and even death. Why were the sharks willingly staying awake, as if they were permanently part of the sleep deprivation study? Why were sharks dying in the aquariums, yet were able to survive with no sleep in the wild? And had this near-apex predator unlocked the ultimate biological cheat code, the ability to prove that, for them, sleep really was for the weak? Since the release of Jaws in 1975, the great white shark became more than just a scary marine animal. It became a global fascination. Audiences were terrified and captivated. Suddenly everyone wanted to see a great white up close. Aquariums around the world scrambled to deliver. If they could host a live great white, it would be a historic achievement, scientifically, publicly, and most importantly to the aquariums, financially. But what followed was a decades-long string of failures. They did everything possible. Custom-built tanks, live prey releases, carefully controlled water temperature and salinity. But no matter how advanced the facility or how young the shark, they couldn't keep a great white alive in captivity for long. The first known capture of a great white for public display occurred in 1976 at SeaWorld San Diego, and the shark lasted a grand total of 16 days. Over the years, other facilities tried too, often with even less than 2 weeks of survival time. One of the most famous attempts came from Monterey Bay Aquarium in California, a facility known for its cutting-edge marine research and advanced life support systems. These weren't just rookies trying to build a tank. They had the resources, they had the experience. In 1996, they wrapped up work on the Outer Bay exhibit. It cost them around $110 million, and it was massive. The tank stretched 90 feet across, went 35 feet deep, and held a full 1 million gallons of water. At the time, it was one of the biggest and most high-tech aquarium setups anyone had seen. Between 2004 and 2011, Monterey Bay had 6 attempts to host juvenile great white sharks. The first one, in 2004, showed promise. A young female shark was caught near Santa Monica and transported to the aquarium. She adapted well at first, swimming steadily and even feeding on live fish. The team was hopeful. But after 198 days, the shark began attacking tank mates. Her health declined and they were forced to release her back into the wild. The next 5 sharks were even bigger failures, some lasting just a few days in the $110 million tank. Japan also gave it a shot. In 2016, the Okinawa Chuarami Aquarium captured an 11-foot-long young male great white. The shark was placed in a massive tank to be observed by a crowd of visitors. The aquarium provided round-the-clock care, careful transport, and expert monitoring. And the shark refused to eat, swam in disorientated circles, and died in 3 days. Other attempts from aquariums in South Africa, Australia, and the United States followed a similar pattern. No eating, erratic movement, visible stress, and always constant swimming. Despite all efforts, no aquarium has ever been able to keep a great white shark alive for more than a few months, and none have done so since 2011. It wasn't just stress, it wasn't just unfamiliar surroundings. This was something deeper, something built into the shark's biology. Even in a quiet tank, with no predators, no current, and no reason to panic, the sharks never stopped swimming. This raised serious questions. Were they swimming themselves to death? Couldn't they just rest like other sharks? Why was stillness such a threat to them? Researchers looked into the mystery, and what they found wasn't a flaw or a failure to adapt. It was the design of the shark itself. The great white was never built to stop swimming. To understand why great whites can't sit still, experts zoomed in on how they breathe. Most fish, including some sharks, can sit motionless and still breathe. They do this by actively pumping water over their gills using muscles in their throat and mouth. Water flows in, passes over the gill slits, and oxygen is absorbed into the bloodstream. But the great whites are different. They belong to a category known as obligate ram ventilators, which, in simpler terms, means that they must swim forward in order to breathe, no exceptions. Here's how it works. Water enters through the mouth as the shark swims forward. The water then flows over the gill arches, where oxygen is absorbed into the blood. Then carbon dioxide is released back into the water, and the water finally exits through the gill slits on either side of the head. If the shark stops swimming, water stops flowing. If water stops flowing, there's no oxygen exchange, and without oxygen, the shark begins to suffocate quickly. For great whites, stopping movement doesn't mean rest. It means death. This is why even when they're stressed, starving, or exhausted, they keep swimming. It's not a choice. It's a life support system in motion. If a great white shark ever gets stuck, like here in this 2019 incident in the Guadalupe Island, where one got trapped in a diving cage, it's basically a death sentence. It couldn't even just sit there and wait for help, because it couldn't push water over its gills to breathe. But not every shark acts like this. Some, like the nurse shark, can lie still on the ocean floor and use special throat muscles to actively pump water across their gills. Others, like leopard sharks and wobbegongs, spend much of their life at rest in coral reefs and rocky coves. These sharks have evolved for a different lifestyle, slower, more sedentary, and less oxygen demanding. Great whites, as you might expect from near apex predators, are instead built for speed and distance. If you're curious about what I mean by near apex predator and not true apex predators, you can check out the video we made a few weeks ago. I'll link it in the description below. Great whites are high-performance predators with streamlined bodies, massive tails, and powerful muscles that let them cruise for thousands of miles in search of food. That kind of design comes with a trade-off. To fuel their high-energy lifestyle, they need constant oxygen. And to get that oxygen, they need constant motion. Now the question becomes, if a great white shark can never stop swimming, then how can it ever sleep at all? At first, experts considered the extreme idea that maybe these sharks just didn't sleep at all. But that defied everything we know about biology. The consensus eventually became clear. Great whites don't sleep or they would die. But they do periods of reduced brain activity. They aren't long, deep cycles like humans experience. Instead, they're short intervals of lowered awareness, like quick power naps, where the shark's body stays in motion, but its brain downshifts into a low-power mode. In fact, their eyes stay open the entire time. Some marine animals use a sleep strategy known as unihemispheric, slow-wave sleep, where one half of the brain sleeps while the other stays awake. Dolphins, certain seals, even some birds. But great whites aren't following the same rulebook. Researchers suspect something similar might be happening. But if it is, the shark's version is far more extreme. Instead of resting safely on the surface or floating in place, a great white keeps cruising through the open ocean, eyes wide open and body in constant motion. Brain slipping in and out of a low-power state. It's sleep, but it's sleep in a way that only a top predator could pull off. This idea gained momentum in the early 2000s, when tracking technology finally caught up with the mystery. Researchers began attaching biologging devices to wild great whites, tiny computers that record speed, depth, temperature, and movement patterns over weeks or months. What they discovered was surprising. At certain times, especially during the night or in deep offshore waters, sharks swam in long, steady lines at lower speeds. There were fewer sharp turns, fewer ascents and dives. It was almost like cruise control. These patterns were different from hunting behavior. The sharks weren't chasing prey or reacting to their surroundings. They were conserving energy. In fact, it wasn't until 2016 that experts recorded a great white named Emma sleeping for the first time in history. Scientists interpreted this behavior as a form of rest. The shark's body kept swimming, providing oxygen through ram ventilation, but its brain activity appeared reduced. There were no signs of heightened awareness or alertness. It wasn't full sleep, but it was clearly downtime. These periods could last for minutes or even an hour, giving the shark just enough of a neural reset to function without full shutdown. It's a delicate balance, resting without becoming vulnerable. And in the open ocean, that balance is everything. Of course, this made me ask the most obvious question of how can a great white continue swimming safely if its brain is partially asleep? Wouldn't this be extremely dangerous for accidentally running into anything? Even when not fully alert, great whites are equipped with some of the most advanced biological sensors in the animal kingdom. Their snouts are lined with tiny electroreceptors called the ampullae of Lorenzini, which can detect the faint electric fields generated by nearby fish or even a heartbeat. Along their flanks, they carry a lateral line system that picks up water vibrations and nearby movement, kind of like sonar for the body. Add to that their powerful sense of smell and motion-sensitive vision, and you get a shark that can stay aware of its surroundings even when it's not fully awake. These kinds of automatic instincts honestly sound like something you would see in an anime, but somehow these sharks pulled it off. Interestingly, while humans rely heavily on rapid eye movement sleep or REM sleep for cognitive functions like memory and dreaming, sharks likely don't enter REM sleep at all. They don't have a neocortex, the brain structure associated with complex thought and dreams in mammals. This means great whites probably don't dream, but they do undergo forms of neural maintenance during rest. This form of sleep is purely functional, not psychological. It's about keeping the body and brain running smoothly without the full shutdown we associate with sleep. So while the great white shark hasn't fully defeated the need for sleep, it has evolved a way to cheat it by grabbing tiny moments of recovery without ever truly resting. And while we humans are still stuck needing a full 6 to 8 hours every night, animals like the great white hint that biology might be more flexible than we thought. If we could somehow figure out how to enter low-power recovery states without needing full sleep, could we work longer hours, travel further, and overall live more fulfilling lives? Well, our brains are a lot more complicated than great whites, so science doesn't exactly point us towards this happening anytime soon. But at least for now, I'm not too eager to be working overtime when I could just be laying in my bed.